Hello, my name is Sam from Hunter Caravan Designs, and I've been trying to make myself an independent swing arm. I've called it the Dust Devil. It's going for 2.8 ton overall ATM. So each arm would be 1400 kilos on the swing arm. So I'm trying to make an entire assembly that will simulate the effects. The only guidelines I've really been able to find are those that are written in VSB 14, section LS for tyres, rims, suspension and steerings, where we see that there's a bunch of different test categories here that we could use, or different forces and guidelines to tests and analyses that we can do. So these are the ones here that we're going to try to satisfy. But first off, for the main design, I'd like to test the entire assembly. So we want the spring, we want the bolts, we want the bushes, we want the hinges, we want the swing arm, we want everything we can in there, except for the we're not going to need the brake drum or the tire or anything. They're going to come from our suppliers' specifications, and we're going to work to their specs on those. We don't really want to double test anything that we don't need to. In our case, however, the entire swing arm assembly is unique for us, so we're going to test it all. The spring itself I wanted to try to rate. In testing, I was loading it with 700 kilos only, half of the ATM that I was intending. And you can see that this spring design here was getting a lot of forces built up into it, and it was distorting in a manner that I didn't want it to. In actual, it won't be bending over like that. We've got bumps and all sorts of things in place to make sure that it can only really bend straight up and down. And also here I was using a mild steel in the beginning. The mild steel calculations, especially on its elongation, its elastic qualities and stuff, are not suitable for what we're doing. In the past, I've had people tell me that this was a mild steel that they were using for these springs, but I saw them in the field and I can tell you now that they were definitely not mild steels. So what we've gone for here is a thing called music wire, which has a very, very high tensile rating. Fantastic for this sort of stuff with springs. It is what most suspension springs are made from. So keep that in mind if you ever do any of your own testing. You can get material quality, you get your mechanical properties for the music wire from sites like MetWeb and other material sites that can give you mechanical properties. Also, just Google them, try to find them that way is always a good way. So here in the next test, I tried to give it a housing, the top and the bottom bumps, but you can see it's still distorting to the side. I had sliders in effect. The bottom there was just a fixed geometry. There's some dicky geometry left on the spring that I'll get rid of eventually for the final testing. But you can see here it's still distorting. I didn't want to put in more sliders and everything like that to get the effect that I was after. So really I just wanted to go and put it in the entire assembly. So here we see now the entire assembly, just a static test. This hasn't been saved into a part, it's done as an assembly. I've got the bearings in, we've got the bolts. We don't have like the camber adjustments and stuff like that. For now we've just gone with the bolts in placement to simulate the fixture. All the hinge bushes are in place. This plate here will eventually mount the shock mounts, obviously, which we'll take into equation in a final test. Again, this is just preliminary. This big fillet on top there, that's a big absorber for a lot of the forces. And here we see like the initial tests that I've done. That outside plate out there is not fixed on correctly. The bonding for it didn't work in this test, so I'll have to fix that up. We see here there's a lot of forces and a lot of high forces. See, I've got the Volmesis set to 350 MPa. The steel was a 350 grade steel. So those red areas are legit problems. The bush, as you can see, the bush isn't a problem. The bush seems to be working well. I've got the properties all set for that correctly. We've used connectors for the bolts and stuff. Well, not a connector, but we've used the actual bolt in location and everything like that to try to simulate it in. And I've just bonded that bolt in, but used it as a non-penetration and such with the other moving components. And The spring, of course, look, the spring is music wire, so the 350 MPa doesn't really, show anything here for the spring. The spring's going upwards in its yield of 2000 sort of thing, so the spring will be blue. It'll be fine. So we'll animate this just to show the forces moving through it. It animates scene by scene, so this can take a little bit of time. Oh, and look, we've got forces already building up. So here at the top end there, we see that force, but that's all right, because what I'm going to do is I'm going to try to make a knuckle that will go over the hinge to absorb some of the forces around the hinge, and we'll see about that force at the end of that fillet, whether or not it's going to, or fin rather, we'll see if those forces, that corner there is going to be a problem, because that bar's trying to bend. This back, the stub axle holding there, it will try to bend with this force, and I put that in place there to try to prevent that, but as a result it's also absorbing all of that force. And that stub axle rod at the rear end there is one full piece of steel. It's not an SHS or an RHS or anything. It's right through steel, so when it bends with a lot of force, and you see that fin there absorbing that ore. We can get around that with like a cutout in the design or something. I would just like to try to drop those forces as much as possible, because in the actual test you saw in VSB 14 our bump loads are 4G, which is, it's going to be a real lot of force to try to pull off safety factors on. I'll do the study to a point where I'm really happy with it, and then we'll have some proper engineers or somebody look over it just to sign off on our findings and everything like that. You'll see in my post down below too that I've spoken about in the past, on my Facebook group rather, I've spoken about the testing requirements and stuff like that. Okay, so our spring's looking good. The spring gets a bit of force build up here at the top, and that's mainly just because I've used a bonded connector there. Again, I could use non-penetrating for this. I'm trying to limit the degrees of freedom. In the intended purpose, in the intended use, it will only move directly up and down like this. There's going to be some bumps that go over the metal bumps, so like a plastic or a rubber. It will help absorb impact. It will also help absorb the actual butting together of like when they bump together, obviously. But these forces building up off these corners, these big red forces here, especially that one at the front there, that's no good. We'll have to fix that up. We want our design to act better than that, and this is just at ATM, so imagine those forces by the time we go to the by4 bump load. Admittedly it'll be a different environment, but yeah, we want to, I'm not concerned about that up the top there at all, because this is all fixed geometry in the actual test. So yeah, when the force comes up there and hits the fixed geometry, it builds up. But in actual fact we have large RHSs and things at the top there that will absorb those forces, as those forces will shoot straight through. And yeah, this plate, not bonded. A lot of force there in that corner. So you can see all these forces, these reds. We're going to try to fix this up. And here we see the fixed assembly. So you can see, yep, I've got these knuckles here on now. My plate on the outside's bonded correctly. I've got this here, so you've still got access to the grease nipple for the hinges. Down the back here, we've added these gussets in to try to help take a bit of strength. They got holes in the front of them because holes are cool. I added some extra steel here to this plate around the spring, and an angle there at the bottom, so that'll hopefully pass some force down. Now a gusset will also help absorb all of those forces that we saw building up in those corners. we saw forces at the hinges as well too. Now our knuckles will absorb a lot of that. So here we go in animation, and already straight away you can see that some of the forces have decreased considerably. All the forces there that were attaching to that stub axle rail, they've all been dealt with now by the gusset, the fillets absorbing a bit better. We want to have a look at this corner for this top fin. The forces are nowhere near as bad in there. We're still getting a little bit of build up there in the corner at top end, but that's, I sort of think that's not so bad. Again, maybe we can put a cutout there or something in the design. We still get a lot of force build up at the top of this fin here where it's trying to dig into the arm there. So I might extend that knuckle through to sit underneath that, so those forces are sort of dispersed by that knuckle plate a bit more. This doubler plate here is doing its job now and absorbing much more of that force. Not seeing anywhere near as much red now, which is great. I'm really happy with these little gussets. Look at it carrying the force there. Little champion. Yep, and the spring, again, this is not accurate for the spring. It shows, the forces moving, which is great. But at the same time, remember, the spring's going to have a yield of somewhere in the range of 2000. So now we'll do an ISO clipping, and we'll try to have a look at exactly where our forces are coming from. Again, the spring is good. The spring is meant to be where the forces are. The spring has high tensile. We're going to roll it back to 0, but there was a lot of action going on in the hinge there. So we'll get back and have a look at that. So here at 0, and now we'll see the forces as they rise. It's only showing us those parts where the forces are. So 100, 175. This is good, but then okay, and that's this is in the range of 290 MPa in these areas. So we see now it's affecting our hinge and the bolt, maybe. So here at top end at the 350, okay, no, it's in our hinge and our bolt. Yeah, definitely the hinge and bolt. Definitely the hinge and bolt, not the bush, I'd say. I don't think those four. We saw as it spanned out, but you see like their green blue forces and everything spanning out in the bush itself. The bush itself should be able to take a lot of force because of its elastic qualities and stuff, and it's housed at the moment, so really crushing it shouldn't be quite an option for these forces, but that's not good that it builds up like that at the front end. A lot of force there seen in the hinge. So let's go to 2000 MPa, which is our high tensile range. So our hinge and our bolt are going to be made out of really high tensile steels, not mild steels. So these are kick-ass ones. I'm going to put all the links for how I got my material details and everything like that down below, so that anybody can cross-reference, check or anything. If you have better material qualities, if you have better mechanical properties, tell me. I love trying to get a better library for this sort of stuff. So here we see we've still got red force. That's above 2000 MPa. But it's only into our bolt there. We can see it. Look, it just dies down, dies down, dies down, out of the hinge and into the bolt. So it's right where the bolt connects to the hinge. And this isn't going to be a huge problem because bolts have insanely high MPAs and yields. So what an 8.8 bolt is meant to be somewhere in the range of, I'll show the data for it, somewhere in the range of, it's like the 8 means 8,000 MPa. So the first number is times 1,000 MPa. The second number, so the first number is times 1,000 MPa and its tensile force. The second number is the percentage of the first number in yield. So an 8.8 is 8,000 MPa with 80% of that MPa in yield, which is crazy high, as you can tell. So And I actually think that's higher. Like they're the standard numbers. So suppliers and actual bolt manufacturers. So here we see there's the grading thing, for your MPA, percentage of MPA. But the actual MPAs we're dealing with are over here. So look at that. That's the range we're going to be in. And that's all. Have fun. Thanks very much for watching.